Hello and welcome. In this video I want to show you the basic installation of the extension Rhino Rotoplate. And my name is Felix Frischmann. I'm from FFR Engineering in Munich in Germany. You can also find all the necessary links on the webpage of ffr/engineering.com. So this document you will see here, you will also find in the installation folder of the Rhino Rotoplate extension, which I will show in a second. First of all, I want to say something about this extension. It is a Python-based extension to allow you to generate NACA profiles or airfoil cross-sections using the software Rhinoceros. Here is the link from Rhino 3D, so a CAD program. And to use this extension you will have to use the Rhino version 5 or higher. And basically we provide an extension consisting of Python scripts and also Python data structures to generate NACA profiles and also use those profiles basically to make wing models and also rotor models. There will be a second video, you will see it in the links below this video, where you will be introduced in how to use this extension. This video now will be only about how to basically install it. There is not a real installation process, but let's call it installation. And this is what we will do right now. Let's jump right into how to use it. I have already my Rhino 5 open, but first of all I will show you here the folder. That will be basically the folder, let's make it bigger, which you will see if you unzip the downloaded extension. You can also use SVN to check it out, and you will see the basic folder you see here with all the files provided. What I talk about here can be also found in the resources and documents folder. You see here two PDFs, one for the usage and one for the installation. So at the moment we talk about the installation process, as we might call it that way. And yeah, and the rest here you see other folders for the script itself. Let's go for example to the profile generator. That's the core of the generation modules provided with the software, and here you see basically the source code, the Python code. And furthermore, you have here some Visual Studio projects which are only necessary for the people who want to maybe extend that software. Even then it's not really necessary to have here the Visual Studio solutions. Nevertheless, they are now provided together with the software. So as I said, there is not a real installation process, basically because it's Python. Of course, you have to be able to import the necessary scripts provided along with the software. We will start from Rhino 5. Let's assume you have it open and you have to be more or less a little bit familiar with the Rhino working process. What we're going to do now at the moment is to use the IronPython extension of Rhino, which allows you to script some of your jobs and also use Python-based products within your Rhino environment. And this is exactly what we're going to do. To do so, you have to type in edit Python script in your command. It's already suggested to you, and what should happen is that here such an, in the first case, such an empty editor will open. I will close that because this is actually what I want to show you. So first of all, you will see something empty, and here of course you can use the Rhino Python to script some of your jobs. So this is your Python IDE, which allows you to script. The easiest way to use this software, I guess, is to have a look at some of the samples provided along with the software. You can find them all if you downloaded and unzipped the folder under resources and samples. Here's also a PDF. Let's open that for a second and show you this document. Here you see also an overview what each of these samples is showing you, or what should you learn from those samples. And you already see here there will be some NACA profiles generated. If you're familiar with the NACA profiles, I guess otherwise you wouldn't be having a look at this module. And out of those you can assemble them to wings and later to entire rotors, including the hub. And here you see an overview of the currently 9 examples, and the 9th one is this more complex rotor model. And they're all provided here in this folder. So let's jump back into the IDE of Rhino and let's open one of those examples. Actually, I will use this folder here, so I'll basically just copy the folder and open one of those scripts for you. And let's say we will have a look at script number 3. Let's see what we'll find here. Now you could of course use any of those at the beginning. Now, so this is now a Python script. You see here at the beginning some of the things related to Rhino. So you import Rhino as Rhino reference and some other things. And now comes basically the only part where you have to kind of install something. As I said, it's a Python extension. There's no real installation. There is no real compiling. Nevertheless, there is something where we have to append the path where you unzipped the solution, which should be known to the environment here. Otherwise, you cannot do what you have to do down here, because you have to import the modules which you provide. So we not provide only kind of scripts which you could copy. No, we provide you real modules and also some object-oriented code. And so you have to use this import statement. You can also always copy those lines. To do so, nevertheless, you have to adjust here in the line 16 to 18 something. First of all, there's a rise not implemented error. I did it on purpose so that people are forced to have a look at those lines. You can basically uncomment it, but then here in this line you have to copy the path pointing to the folder. So basically to the folder, to the top folder here. And let's just copy this one here, edit here, fast make the slashes in a Linux style, so not in the Windows style, and that's already it. So here you have downloaded the solution to, and that should be everything necessary to run the script. Let's see what happens. We basically just started to run it, and here let's change the view to rendered. You see that this model was generated with the help of the commands coming here down in the script. What those commands mean and how to use them will be explained, as I said, in the next video, which will be about the usage process. Nevertheless, I will want to, after I said that there will be this installation guide also provided with the software, I want to also point your attention to some of our other products in the area of propeller design and in the area of this propeller shape optimization. It's a software called Prop Design. Prop Design is actually a really awesome kernel by Anthony Falzone. Here is the link for you. But we made some redesign and integrated it into some UI and also some interfaces with CAD systems and CAM systems. And this is about to be finished and released, and if you're interested to be also on this mailing list, then you can write us an email to this address down here to let us know that you want to have some information about this software as well. And if you have any questions, don't hesitate to contact us. Thank you very much, and as I said, you will find down in the comments the link to the next video explaining you the usage of the extension. Goodbye. Hello and welcome to the usage manual of Rhino rotor blade. So my name is Felix Frischmann from FFR Engineering. Also check out ffrengineering.com for further information. We are a company from Munich, and in this video you will see how to use one of our software, which is basically an extension to Rhino, the famous freeform CID system. In this video I want to show you how to use our software, what is it doing, how can it help you, and give you some idea on how to exploit the extension for your purposes. There is also another video where you will find out how to basically install the software. There is no real installation process. Nevertheless, there are some little things you have to adjust to use our software, which is Python based. And this video you will also find in the link below in the comments, and also on our webpage, where you find all necessary further information on this and other of our on also other softwares which we have. Yes, so let's come back to a Rhino rotor blade. As I said, this is a Python code. It's actually an object-oriented Python code with modules and real data structures. There are mainly 3 generators at the moment, a so-called cross-section profile generator, mainly for NACA profiles. You should be familiar with the term NACA. This is basically the profiles used for many wing shapes. And out of those are also wings and rotors possible to be generated using our extension. So this is built up hierarchically, so that NACA profiles are basically consisting of 2 curves, an upper and a lower curve, and they themselves are built from sample points. That's the standard way how to build the NACA profiles. And then those cross sections or airfoil cross sections can be assembled to form a wing model. This is the wing generator, and then there's a third generator, the rotor generator, to take those wings and bring them together in form of a rotor, including also a hub. You can also see this here on the slide, and all these slides are also provided to you if you download the folder with the extension. We will have later a look at it, but here you already see there are basically 3 steps. There's the step where you have the NACA profile generator, and then you can assemble them here to a set of cross sections forming a wing model, and then if you assemble those wings and add a hub in the middle, you have a rotor model. That's basically the idea of the extension. And yeah, let's go to the basic NACA airfoil profile generator. It's not necessary that those are NACA profiles. You will see if you look at the code, you can basically also find some other things like circular cross sections. You can extend it by your own ideas, but of course the main purpose of this extension was to have NACA profiles, and at the moment there are 4-digit series and 5-digit series provided for you. So these are terms from the NACA world for different series, how to generate the cross section, the airfoil cross sections. And at the moment you have those 2s and also circular cross sections. You can extend that, and we also plan to extend in the future the set of provided cross sections by more flexible things and more maybe different cross section possibilities. But nevertheless, at the moment there are those options available already, and you will see that you can use them to generate some nice wing and also rotor models. If you use this cross-section generator, we will have a look at that later in the code itself, then you will see that if you generate only one airfoil cross-section, that it will be consisting of an upper and lower curve to form this airfoil cross-sections. And when you generate it, there are some arguments like a length parameter and a thickness parameter. There might be some more depending on your digit series, but basically most importantly is the length and the thickness parameter. The length for the chord length, and the thickness, which is also basically defining the name of the NACA airfoil, if you might know it. One important thing is that we work here in the Rhinoceros CID system, of course, as you will see in a second. And in this you consistently work with coordinate transformations and construction planes. Some people who are more familiar with products like NX or I don't know, Inventor, they might be more used to the sketch-based approach on how to draw. Here in Rhino it's different, you have a real freeform system, nevertheless you have construction planes, so everything is designed on the construction plane unless you define it differently. And the same holds here. What we do is that we basically give basic local coordinate system to the airfoils, and you can change that. We call this transformation, so you can apply a custom transformation if you want to have this airfoil here in a different location in space, but you have to actively do that. If you don't do that, you have a default coordinate system where this will be drawn. And everything will be with respect to this sketch origin point or the tip point of the airfoil. And yeah, then you have this coordinate system. Here you see a picture, and you can also see it in the example one, which we have a look at, that you can apply those transformations to transform such an airfoil in a different construction plane. So if you look at it mathematically in a different local coordinate system. And here we provide some utilities to make that more or less smoothly for you. And you will see that in the code itself. Let's jump to the wings. So the wings are, as I said, consisting of cross sections. So they're an assembly of cross sections. And there are some basic arguments also for the wing generation, like the wing length and again some wing transformation. Let's have a look at that in a second. But yeah, important is that you have here such a wing model where you consequently add some of the cross sections after each other, and then of course you can define from those cross sections a wing by sweeping along this cross sections to form a surface model. I guess this is what you want to have if you make some, for example, finite element analysis or something else. So you need a surface model, maybe even a solid model, but a start for that is a surface model, since Rhino is a BREP modeler, and thus you produce a model using here different cross sections. Of course, then it's important here that you make something senseful by adding the cross section. So of course you can make something not valid here. We simply assume that you as an engineer have of course the right approach, since you might also be working with Rhino a lot, to do something senseful, and the script will help you with that. So here we have the wing longitudinal direction, and we call it later the X position along the wing. And we also have the wing root point here again, which is here in the tip of the basically first cross section added. And then we have again those transformations. So similar to the airfoils, if you look at them separately, of course the same holds for the wing in total. We can apply on the generation of a wing instance. We can apply a custom transformation to bring the entire wing in some local coordinate system. And by doing that, this transformation will be inherited by all the airfoil cross sections you add later in the code, and we'll have a look at it. So basically we have to make this step only once. This is a Python code, and you will see it later, which is quite flexible. You can come to the same point by different means, of course. And since it's open source, you can also extend it the way you want. Here I just show the process in the way as it was intended by me as the author of the library, and yes, and some of the convenience tools to do that. And here the convenience is that you can only apply the transformation once, and then it will be added to all the airfoils itself. Again, on the adding an airfoil cross section to the wing model, which we will see later. Yeah, and this is here described, but we will have a look at the code. Basically, I only want to point your attention to this add profile. This is a command from the source code where you add one, I'll go jump back here, where you add, for example, here this cross section to the wing. Of course, now it's important that you add them after each other according to their position on the longitudinal wing direction. This is what you will have to do. And here I have already some pictures of those local transformations. What is that? So, as I said, when I will jump back here, when we make an instance of the wing, you give them a basic transformation. This basically defines the basic position of the wing in space. But now you also add, again with this add profile command, one of those cross sections to your wing. And while doing that, you might want to have some change of this position, some local change of this position with respect to the root wing point. Yes, assume you want this wing to have some kind of a bend here, and you will see it on the pictures. And then each of those cross sections that you have to be added with respect to the base point or base cross section with some either angle or with some translation. And this is exactly what we do when we apply here this local translations and also rotations to the cross sections of the wing. And you see here the pictures which will help you to understand in which direction basically you apply those transformations or rotations. So this is a vector of 3 values. Actually, you don't see a picture here for the third value because this one is the one, and you will see it in the code, which you kind of always have to use, because this third value will define the position on the longitudinal direction of the wing where you're at your profile. So this is the first value here. This one has to be always given to make a valid wing model, as I said, because those cross sections have to be added in the order with respect to their position along the wing model. Now you might ask, this process could be automized. Yeah, you're right. Of course, if you know the wing length and if you know how many profiles you want to add, then you have here the position, the X position along the longitudinal direction. Nevertheless, at the moment, this is not done for you, so you still have to simply add that. That's very simple. You can have a look at the sample codes provided with the software. And we do that because some people might want to play around a bit here. So maybe at the beginning, where you have a bigger change of the geometry, you might want to have a closer network of the added cross section, and maybe in the back you want to have more space between the cross sections. This is why we give you the flexibility. But then there are the first 2 values in this vector here, and for example the first value gives you the possibility to add some in-plane translation. So in this picture we added something increasing with the distance from the root, and you see like that here the deformed orange shape, that you can produce a shape going in this direction, this in wing chord length direction. And if you play around with the second parameter, you apply something going out of the wing plane. And then there are some rotation values, for example the wing skews. I will start actually with this value here, the third value. Again, it's some vector, and the third rotation gives you here the skew, I would call it, the wing skew, where each of those profiles get some rotation with respect here to the root point, so to say, in the plane defined by the airfoil cross section itself. There are 2 other rotations which are not so natural, and you also see here not a real picture because it's actually a bit hard to depict. For example, the second value, you have some bend of the profile in this axis here. So it means this 2 profiles here will not be parallel to each other. And here the same holds there, where they will also not be parallel, but they will be simply in a different rotation axis. These 2 rotations are maybe more usable in combination with the translations here, or in combination with the bends. The bends are also a parameter which you can use while adding a wing, and the bending, I call it, is here given by 2 values. It's a bending out of the plane and it's a bending in the plane, so a bit similar to the rotation, but nevertheless a bit different. And here you simply can use an angle to produce also this kind of bending. And now you can think, of course, that if you here again apply also a rotation plus a bending, then it might make sense again to have both values here, or both transformation patterns separated. So this is the wing generator, and now we come to the rotor generator. You have already, I guess, an idea that basically now you can just simply combine wings to form a rotor. That's exactly what's happening. You define the number of wings, and again you have something like a rotor transformation. What is that? Well, I guess you assume already what that might be. and is correct. So you have basically a transformation applied to the entire rotor model, but now, and we will see it in a second, it's with respect to a different point. There are other two parameters like the hub parameters here. So what is the hub height, the hub diameter, and also the type here of the topping. Is it rounded or is it like a tip here, like a pointy tip, or is there no topping at all? And like this you can automatically generate this hub model as well by using the rotor generator. So the transformation, as I said, is important. So the rotor transformation is actually applied to the base point of this cylinder here, which you can't really see. You have to be transparent. So the base point of the cylinder, the center point, is the root point for the rotor model. And then you have the wings added to the rotor, and then again each wing has the root point here, because this is simply taken from the wing assembly as we've seen before. That gives us the flexibility to make again or play around with these transformations. So you can, on the generation of the rotor, apply some transformation to the rotor itself. You can bring the entire rotor into a different coordinate system, but also you can play around with the wings itself, as you have seen before. And we have again these pictures here, which basically mean the same, and nevertheless I added them. So when you add the cross sections to a wing of the rotor, you can apply, of course, the transformations you have seen before, and like that generate something you see here with the translations of the rotations. Here you see actually a picture how this rotation is doing here, as I've tried to describe before. And here you see it also more clearly how the rotation is applied in contrast to the other wings which have not got this transformation. And here you also see the flexibility, so it's possible to apply this transformation only to one of the wings, because we make here the possibility to add the profiles to each of the wings and applying transformations to each of them separately. And here you see again the bends. So this allows you to generate some nice rotor models, and we now have a look into the code itself for a second. I first want to, before I stop this presentation, point your interest also to one of our other softwares in the field of propeller design and propeller shape optimization. It's called Prop Design. It's actually a redesign of the kernel written by Anthony Falsone. You find here the link to his webpage and his awesome code. We took the code and packed it into some graphical user interface and some exchange to CAD systems and also to FEM programs, and thus it allows you to optimize with some semi-analytical computations the shape of a propeller for you, and then you can further use these models in a CAD or FEM process to produce or design the propeller. If you're interested in this, just write us an email here to this mail address. It will be also found in the comments under the video, and then you will be added to the mailing list. The software is not yet released. It will be released very soon, and then you can get the latest information. Enough with the presentation. Let's jump directly for a second into the Rhino models and model generators. As I said, this video is about the usage. There's another video about the installation. I will not go into detail again. Let's assume you managed to unpack this folder, which can be downloaded or checked out with SVN, and you managed to open your Rhino and manage to type in edit Python script to start the IDE. Let's start here from a zero script. And as I said before, the easiest way is really to have a look at some of the samples, and I will again take the sample number 3, which I also use in the installation guide for this Rhino. Actually, it's already the correct path. Let's use this sample number 3, and as I said before, you will have to wait a second. As I said before, you will have to adjust those lines 15, 16, 17 to make the code run directly, and this will be seen in the other video. So what comes now is usually that you have to make some imports. These are all imports pointing to our extension, and you can usually just copy those lines into your own script from the samples here. If there's something missing, run one of our models and see if there might be one of those imports missing, but usually this should be complete. What's happening now? In this model, let's maybe run it first. You see what happens. You see something is generated. Let's jump to Rhino and let's see in the rendered view what is generated. It's actually a wing model. You have 1, 2, 3, 4 airfoil cross sections, and you see they also have some relative displacements with respect to each other, so some rotations and translations. All this is happening in this script. So this is now starting from the wing generator. I could start now from the profile generator. I won't do it because actually you will see in the script that we also apply, of course, the profile generator. So here you define the origin point and the directions which will give you the basic transformation of the wing. This is the local coordinate system of the wing. It consists of a point, which is the root point of the first airfoil cross section, and some plane or some directions to define a plane. This is the transformation which will be used in this line here to be passed to the constructor of the wing generator. So the wing length is 400 with respect to the units you have in your drawing, and then you have a wing model with this wing generator, and this inherits automatically then the transformation defined here. Now you start adding, in this case, 4 airfoil cross sections. So here you actually use then the airfoil generator, the NACA generator for airfoil cross sections. Here a 4-digit series, and here in the init you pass the parameters of chord length and thickness ratio, which I showed in the presentation. And you do this 4 times. So here you only generate those cross sections, but then you also add them to the wing model. This happens here. So here you call this add profile, which I mentioned before, this add profile member function of the wing generator, and add one of the profiles to this model. And the first one you add, of course, at the root point of the wing. You could also do it somewhere else, but let's assume it makes sense to add it at the root point of the wing. And the second, third and fourth one, of course, you add with a rotation and translation vector. The rotation vector could be 0 if you don't pass it. You could also add a bend here, so you see the bend is not passed. The rotation could be also left out, and then you simply don't pass it and then assume there is no relative rotation assumed for this certain profile, which is added now. But what should be always added is here the third value. As I said, this one defines the longitudinal position of the wing model. So we could, for example, here say we have no local rotations, and actually these ones here, they should be actually 0. So we don't want to have any kind of translations except the third one. So this one is the important one on the longitudinal direction of the wing, but the other two which you saw on the slides, which are something like in plane and out of plane translations, they should be 0. And if I didn't make a mistake now, no I did not, you will see here that this model here which is generated is similar to this one, with the difference that you don't have applied any kind of rotations and translations. You see there are some translations going out of the model, and you see some rotations like a skew. So this is basically how you generate a wing. If you look, for example, into the number 4, I think it should be, let's have a look at that. It's a more complicated model. If you go to the samples, you also see here a PDF, and in this PDF you see an overview. So number 4 is actually something like a turbine, a wind turbine blade, and I will not run it now. I will just want to show you that here we do basically the same steps. We generate a wing, and then we basically add the wing cross sections. But now we don't do them like before, that we make them hard coded and add them, but we make it in a loop. That makes sense, of course. So we have a number of profiles we want to add, 50 for example. And then of course, as I said, you can define the X position here along the wing, and then we add some of the profiles, and the profiles are here, for example, changed. So depending on the position on the longitudinal direction, you have, for example, at the beginning a circle, then later you have a 4-digit series, and then you have another 4-digit series. And also you can use some functions which define how the, for example, rotations or translations are given. Let's assume, for example, you have a linear change of the translation with respect to the longitudinal direction. It's easy to make a Python function for that. We provide you with some templates which you can have a look at, but it's easy to write also your own functions and use them to define the translations with respect to the position along the longitudinal direction of the wing, which is the most natural way to describe it. And if you use this kind of methods also in the rotor model, you can generate something like the model 8 or the model 9, for example. Let's have a look at the model 9. So the difference is now that we don't use the wing generator, but we use the rotor generator, but you see it's just hierarchically seen the next logical step. So here you basically use the rotor generator, not the wing generator. But the same, you have a local transformation, and now you have different parameters like the rotor radius, the number of wings, and some parameters for the hub shape. And then the next step is to add the wings, and each wing can have a transformation itself. That's important. And then you add here in a double loop, you run over the number of wings and you run over the number of profiles within each wing, and you add them here again to the wing model, and the wing model is the wing within the rotor, and again you can apply your local transformations. You see it's rather a short script, and nevertheless it allows you to generate a nice model. I will actually show you. I will delete this one here and basically run the model. The only thing I have to do is to copy those lines here to make the extension known, as I explained in the other video. And if I do so, you will see that the model will be generated. You see it can be a process taking a bit of a time, depending especially how many profiles you add to the wing model. But if you succeeded, and it will be done in a second, you see that you can, with a few lines and with those utilities you provide, generate some rather complicated structures. So still have to wait a second and now jump to the model itself. Sorry for the delay here. Now you see it's quite a model where probably you added a little bit too many profiles here. The performance is not the best, but you see here you can generate something more complex with rather a few lines of code. This is what the extension should do for you, and I hope you have fun doing that. We appreciate to be cited if you use this extension in a commercial way or for academia, and thank you very much for your attention. Goodbye.